Welcome to session 11 of UGBS 301, and in this session we shall continue with our studies on hypothesis testing. We already know the definition of a hypothesis testing, and we said it was a test that involved making inferences about a population parameter using a sample statistic. In this section, we shall also continue to formulate and test hypotheses and make conclusions regarding the results of the test. After this section, you should be able to test the hypothesis or form confidence intervals for two independent population means. And under that, we are going to look at situations where the standard deviations for the population are known, and then the standard deviations for the populations are unknown. We're also going to look at testing hypotheses to compare means from paired samples. Then we also look at testing the differences between two population proportions. So, for the first part, in testing the difference between two means, you are looking at whether the mean value for a certain group is the same as the mean value for another group. These groups are assumed to be independent groups. In other words, the people present in the first group are not the same people present in the second group. For example, if I want to say that I want to test the performance between accounting students and finance students, then perhaps after a certain examination, I want to compare the average score of the accounting students with the average score of the finance students. So, will there be a difference between the accounting student score and that of the finance student score? And using the same situations I discussed already, we are going to look at situations where standard deviations are known, and then when they are unknown, and then when the sample sizes are large or when they are small. So, for independent samples, we could also have a lower tail test, an upper tail test, or a two-tail test, as we saw in the hypothesis, in the introductory stage of hypothesis, that's session 10. And for a two-tailed or a lower tail test, we have our null hypothesis, which will be stated as the mean for the first group, or mean for group 1, which is mu1, is greater or equal to mu2, that is the mean for the second group. The alternate hypothesis will be formulated in this way, that mu1 is now less than mu2. In other words, we can say that mu1 minus mu2 is greater than or equal to 0 for the null hypothesis, or mu1 minus mu2 is less than 0 for the alternate hypothesis. For the upper tail test, we are testing the alternate hypothesis that mu1 is greater than mu2. In the lower tail test, we tested the alternate hypothesis that mu1 was less than mu2. In the two-tail test, we are testing the alternate hypothesis whether mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0. In testing for this hypothesis for these independent groups or samples, for a situation where your sigma 1 and sigma 2 are known, that is where your population standard deviations are known, we are going to use a z-test statistic. If they are unknown but the sample sizes are large, we're still going to use a z-test statistic, but then we will estimate our unknown population parameter with the sample standard deviation. If they are unknown and they are very small samples, then we're going to use the sample standard deviation to estimate for our unknown sigma, and then go ahead and use a t-test statistic and a pooled standard deviation. Therefore, our test statistic for situation where sigma 1 and sigma 2 are known is given as z is equal to x1 bar minus x2 bar minus mu1 minus mu2 all over sigma 1 squared over n1 plus sigma 2 squared over n2. In situations where sigma 1 and sigma 2 are unknown but the sample sizes are large, we're still going to have our z to be x1 bar minus x2 bar minus mu1 minus mu2 all over. This time we are going to replace our sigma with the sample standard deviation, which is s1 squared over n1 plus s2 squared over n2. In the last situation where sigma 1, sigma 2 are unknown and then our sample sizes are small, we're going to have what we call a pooled standard deviation. The pooled standard deviation is actually calculated by finding the square root of the first sample size, or the sample size for the first group, minus 1 times its standard deviation squared, that is its variance, plus the sample size for the second group, that is n2 minus 1, multiplying its standard deviation squared all over n1 plus n2 minus 2. This gives us the pooled standard deviation and is taken into consideration in the formula. So therefore, our test statistic becomes x1 bar minus x2 bar minus mu1 minus mu2 all over the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. And this follows a t distribution with degrees of freedom giving us n1 plus n2 minus 2. This rejection and acceptance region considerations are similar to what we considered when we were looking at the one sample situation in session 10. So for a lower tail test, we have a negative z alpha, that is our rejection region lies to the left of the normal curve. For an upper tail test, we have a positive z alpha, that is rejection region lies on the right of the normal curve. And then for a two-tail test, we divide the value of alpha by 2, and then part of it lies to the left and then the other part lies to the right. Let's calculate, or let's take an example. Assume that you are a financial analyst for a brokerage firm and want to find out whether there's a difference in the dividend yields between the stocks that are listed on the New York Stock Exchange and then the NASDAQ. Therefore, you collect the following data. For the NYSE, you collect 21 samples. For the NASDAQ, you collect 25 samples. And then for the NYSE, sample mean is 3.27. Sample mean for NASDAQ is 2.53, with standard deviations being 1.3 and 1.16 for NYSE and NASDAQ respectively. Our question is this: assuming equal variances, is there a difference in average yield? Remember that we didn't say that is the yield for NYSE greater than NASDAQ, or is the yield for NYSE less than NASDAQ? All we said was, is there a difference in average yield? This would inform how we formulate our null and alternative hypothesis. Our test statistic, therefore, since we have smaller sample sizes and then unknown population standard deviations, we're going to use the pooled standard deviation situation. Therefore, we know that our sample size, or our test statistic, is giving us, we're going to have the test statistic giving us x1 bar minus x2 bar minus mu1 minus mu2 all over sp times the square root of 1 over n1 plus 1 over n2. And in calculating the pooled standard deviation, you see that n1 minus 1 is the same as that of the sample size for New York Stock Exchange, that is 21 minus 1, times its standard deviation squared, which is 1.30 squared, then plus n2 minus 1, which is also that of NASDAQ, 25 minus 1, times the square of its standard deviation, which is 1.16, divided by n1, which is 21, plus n2, which is 25, minus 2. And hence we have 1.2256. So we put it back into the test statistic formula, and we have 3.27 minus 2.53 minus 0. Because we are assuming that the null hypothesis is true, we would always assume that mu1 and mu2 are the same, and hence the population differences will be 0. That is why we have a 0 here. Over 1.2256 times the square root of 1 over 21 plus 1 over 25, which gives us 2.040. Note that our alternate and our null hypothesis was stated as mu1 equals to mu2 for the null, and then mu1 not equal to mu2 for the alternate, because we wanted to find out whether there was a difference in average yield. Our degree of freedom is 21 plus 25 minus 2, which gives us 44, and then our alpha value is 0.05. From our t-tables, our critical value is t alpha over 2 because it's a two-tailed test, and it's giving us 2.0154. So you see, on the left side we have negative 2.0154, and on the right side we have positive 2.0154. Our test statistic actually gives us 2.040, which is bigger than our critical value. And therefore, since our test statistic falls within the rejection region, we are going to reject our null hypothesis at the 5% level of significance and conclude that there is a difference, or there is an evidence of a difference in the means. So this is how we look at formulation or testing hypothesis for independent samples. In case of paired samples, we are looking at a situation where the number of elements, or the elements present in the first group, is the same as the element present in the second group. That is why they are called paired samples. We actually also do this by considering the pairs of the elements in each situation. And for this situation, our test statistic is giving us t equals to d bar, where d bar is the differences in the scores of the pairs of values, minus mu d, which is the average value of the differences, over the standard deviation of the differences divided by the square root of n. As a general or a simple overview for paired samples are mostly used for more like a before and after kind of situation. For instance, assuming I want to test the efficacy of a drug, the normal thing I would do is to weigh somebody or a group of people before applying the drug for weight loss, and then weigh them once again after some time after applying the drug. In doing so, I want to find the differences for before and that of after. If the drug is very efficient, then we expect that the weight of the individual after the drug has been applied should be significantly less than the weight of the individual before the drug was applied. In testing for these paired samples, we also have the same lower-tailed, upper-tailed, and two-tailed test situations, where for the lower-tailed test we have mu d. For the alternate hypothesis, mu d is less, and you see that the statistic lies to the left, or the critical value lies to the left of the normal curve. For mu d being greater in terms of its alternate hypothesis, that's an upper-tailed test, the critical value lies to the right. And also for the two-tailed test, we have dividing alpha by 2, one of them lying to the left and then one also lying to the right. Note that this follows a t-distribution that has a degree of freedom of n minus 1. Let's take an example. Assuming that you send your salespeople to a customer service training workshop, we want to find out whether the training has been effective, and therefore we collect the following data on 5 salespersons. We registered the number of complaints before they attended the training, and for person CB, they recorded 6 complaints, TF recorded 20, MH recorded 3, RK had no complaints, and then MO had 4 complaints. After the training, we also record the number of complaints that each person had registered. CB now recorded 4, TF recorded 6, MH recorded 2, RK still no complaints, and then MO recorded no complaints. What we really want to find out is that whether the training has become effective. In doing so, we want to take the differences, that is after minus before. If we do after minus before, then we are looking at the number of complaints after minus the number of complaints before. And these are the differences that is denoted as DI. So the difference for CB is -2 because we saw a reduction in the number of complaints. 4 minus 6 gives us -2. For TF, 6 minus 20 gives us 14, -14. For MH, 2 minus 3 gives us -1. For RK, 0 minus 0 gives us 0. And for MO, 0 minus 4 gives us -4. Therefore, we have an average difference of -4.2 with an associated standard deviation of 5.67. We want to find out whether the training made a difference in the number of complaints. Whether the training made a difference in the number of complaints. So, we are not sure whether the training actually reduced the number of complaints, or we are not saying that we want to find out whether the training increased the number of complaints. All we are asking for is, did the training make any difference in the number of complaints? And therefore, our alternate hypothesis would be that μD is not equal to 0. That is, the average of the differences should not be equal to 0. Against the null hypothesis that μD is equal to 0. If μD is equal to 0, then we will say that the training has not made any difference. But if μD is not equal to 0, then indeed our training has made some difference. At an alpha of 0.01 and then a calculated D bar of -4.2, we calculate a critical value, which is also giving us a t statistic with an n-1 degree of freedom, and that gave us 4.604. You can do this from the t table. We have a test statistic that says d bar minus μd over the standard deviation divided by the square root of n, and that gives us -4.2 minus 0, since we are assuming that the h naught is true, divided by 5.67 divided by the square root of 5, and that gives us -1.66. If you test or compare the value of the test statistic to the value of the critical value, you realize that this falls within the acceptance region. That is to say that our -1.66 is greater than -4.604, and then it's also less than +4.604, and hence our t statistic or our t calculated is not in the rejection region, and hence we reject our null hypothesis, and therefore conclude that there is not a single change in the number of complaints, and therefore the training has not made any difference in the number of complaints at the 0.01 level of significance. If we are supposed to formulate other hypotheses for this based on, say, whether the training has been effective, then if the training has been effective, then we expect that the number of complaints before should be more than the number of complaints after. That is, we expect a reduction in the number of complaints. Therefore, if we did a difference of after minus before, then we expect that our mu D should be negative or less than 0. So if the training has been effective, there should be less complaints, and hence our mu D should be less than 0. That is how to formulate the null hypothesis. Given this situation, how to formulate the alternate hypothesis, given this situation when the training is effective. But in this question, we said we wanted to find out whether the training has made a difference, and therefore we opted for the two-tailed test. Now, for population proportions, we want to form a confidence interval or test a hypothesis about the difference between two population proportions. In session 10, we looked at one population proportion. Also, our assumptions still hold. N1 P1 should be greater or equal to 5. N2 P2 should be greater or equal to 5. N1 1 minus P1 should be greater or equal to 5. And then N2 1 minus P2 should be greater or equal to 5. Where the 1s and the 2s represent the first group and then the second group respectively. The point estimate for the difference is actually P1 bar minus P2 bar. And our confidence interval for the population proportion or the differences in the proportions is actually P1 bar minus P2 bar plus or minus Z alpha over 2 times the square root, that's our standard error, giving us P1 bar into 1 minus P1 bar over N1 plus P2 bar into 1 minus P2 bar over N2, all under the square root sign. Under our hypothesis testing for two population proportions, lower tail test, we are going to have an alternate hypothesis of P1 less than P2. And then for the upper tail test, we have P1 greater than P2. And then for a two-tail test, P1 not equal to P2. We can also calculate what we call the pooled estimate for the overall proportion, which will be given as N1 P1 bar plus N2 P2 bar divided by N1 plus X2 N2, where N1 P1 is actually the same as X1, that is the number of successes, and then N2 in group 1, and then N2 P2 is also the number of successes in group 2, also denoted by X2. So, our test statistic for P1 minus P2, or the differences in our population proportion, is giving us P1 bar minus P2 bar minus P1 minus P2, which is assumed to be 0, divided by the square root of P1 bar into 1 minus P bar into 1 minus P bar over 1 over N1 times 1 over N1 plus 1 over N2. Note that this P bar is the pooled estimate for the overall proportion. Let's take an example. In a random sample of 36, 36 out of 72 men and 31 out of 50 women indicated that they would vote yes to a certain proposition. Test at the 0.05 level of significance if there is a difference between the proportion of men and that of women who vote yes on proposition A. Therefore, our test is that we want to test whether there will be a significant difference between the proportion of men and that of women. Because we've indicated whether there should be a difference, and we don't know whether that of men is more than that of women, and it indicates vice versa, we just indicated a difference, and it means that we are having a two-tailed situation where we would make a claim that P1 minus P2 is not equal to 0 for the alternate hypothesis, or we can state that P1 minus P2 is not equal to 0, that's alternate hypothesis, and then the null being P1 minus P2 equal to 0, or P1 equals to P2. The sample proportions are given as P1 bar, which is 36 out of 72, which is 0.5, and then P2 bar is 31 out of 50, which is 0.62. The overall pooled estimate is actually x1 plus x2, where x1 is the 36 for men, and then x2 is the 31 for the women, over the total n1 plus n2. So we have the pooled estimate being 67 over 122, which gives us 0.549. With this information, we can now confidently calculate our test statistic, which gives us negative 1.31. Using alpha equals to 0.05 and then a two-tailed test, we have a critical value of plus or minus 1.96, and then we have a calculated value of minus 1.31, which falls within the acceptance region. That is, negative 1.31 is greater than negative 1.96 and is less than 1.96, and hence it falls within the unshaded portion, which is not the rejection region, and therefore we do not reject our null hypothesis and make a conclusion that there is not a significant evidence of difference in proportions of women who vote yes and that of men who vote yes. There are some examples in this recommended text, and I hope you can try your hands on them and then become skillful in the area of hypothesis testing. This brings us to the end of session 11. Thank you.